A very good afternoon to all of you. This is the last topic in Unit 5, that is multiple dosage regimen by two compartmental open model. So, before going to learn this two compartmental open model through this multiple dosage regimen, you have to learn about loading dose and maintenance dose of a drug. So, what do you mean by loading dose? Loading dose is nothing but the beginning dose of a drug, or also called as initial dose of a drug. In pharmacokinetics, a loading dose is an initial higher dose of a drug that may be given at the beginning of the course treatment before dropping down to a lower maintenance dose. So you just remember two things here. What is the purpose of loading dose and what is the purpose of maintenance dose? Seema, loading dose is nothing but your initial dose. So here our response is going to be started from here. So this is called your loading dose. After some time it will be sustained. Your action is getting to be sustained. So the steady state level to be achieved through this maintenance dose. And with the help of this maintenance dose, you may achieve proper therapeutic level of the drug. So the therapeutic level of particular drug can be achieved through this maintenance dose at the steady state plasma drug concentration level. And the loading dose is the starting or initial or beginning dose of the drug in the course of a treatment. A loading dose is most useful for drugs that are eliminated from the body very slowly. See, when your loading dose is required, this loading dose can be useful for the drugs which can be eliminated from the body relatively slowly. So generally, which type of drugs can be eliminated slowly? For example, I am telling you, when you take cardiac glycosides, the example for this is digitoxin. It will be eliminated from the body very slowly. So in this case of the drugs, you can prefer the loading dose rather than a maintenance dose. Okay, so this drug can be eliminated out very slowly from our body. That is, it is having long biological half-life. If your drug is slowly eliminated from our body, in the sense, what does it mean? It is having some long biological half-life. Because of the long biological half-life, it can able to survive much more time in our body. So, such drugs need only a maintenance dose in order to keep the amount of the drug in the body at appropriate therapeutic levels. See, I already told you maintenance dose is useful for producing therapeutic effect. So in case of some drugs, those may get eliminated very slowly because of its long biological half-life. Because of its long biological half-life. So for that reason, you can take directly the maintenance dose instead of taking that. See here, I told you reversibly. See here, it's not correct. In that cases, you can take maintenance dose. You can take maintenance dose to produce proper therapeutic effect rather than the loading dose. Okay, so because of the slow elimination process of these types of drugs, because due to its long biological half-life, we can negotiable its loading dose. Loading dose is nothing but the beginning dose of a course interval. So we may call it as loading dose. In such reasons, we can take maintenance dose to achieve proper therapeutic effect at steady state plasma drug concentration. At steady state plasma drug concentration. The time required for the drug to to a steady state plasma level is dependent mainly on its elimination half-life. If the drug is not properly eliminated out, okay, if the drug is having more residence time in our body, it would be totally dependent upon its elimination half-life. Then it is also the important factor for drug accumulation property, and maintenance rate of drug administration is equal to rate of elimination. So here you are administering your drug at maintenance dose levels, so it is equal to its elimination half-life. So your maintenance dose at the steady state plasma drug concentration is equal to the elimination rate. Equations for knowing this multiple dosage regimen through two compartmental open model, we need some equations. These equations can be developed for determining the average concentration of the drug that will follows a two compartmental open model, which is similar to that of one compartment open model. So we need to understand the system properly, or we need to what is that, we need to derive some pharmacokinetic parameters, we need some equations. So these equations can be developed to determine the average plasma drug concentrations of the drug, which will follows the two compartment open model, which is similar to that of one compartment open model. So when the distribution phase of one dose is approximately completed before the next dose is to be administered, I already told you, make sure that if you have to take first dose, then you have to take second dose after complete elimination of this. After complete elimination of this first dose, you can take this second dose. So when the distribution phase of one dose is approximately going to be completed, then you can take the next dose which is to be administered. Under these conditions, you can substitute, instead of, you can substitute in place of beta. In place of beta, you can substitute with K. K is nothing but your KE, elimination rate constant. And in case of volume of distribution, you can substitute with volume of distribution area. So these two parameter substitutions may be useful to adapt your one compartmental equations to the two compartmental systems. See, we already learned about multiple compartment models, right? So in that multiple compartment models, we have derived one equation through this mass balance equation. So in that, we will get some hybrid constants like alpha and beta. Have you remembered that? So in that derivation, the last equation is minus 2 beta by 2. So here this is an hybrid rate constant of elimination process. This is an hybrid rate constant for elimination process. Now also we are speaking about two compartmental open model with the sense of multiple dosage regimen. That is the next issue. But we are talking about only the two compartmental open model. That's why here this beta came again. So this beta is need replacement with this KE, elimination rate constant. Why? Because the beta hybrid constant is standing for its elimination output. So for that reason, your beta is replacing with your KE, elimination rate constant. And in normal two compartmental open model, we can take this volume of distribution. But here we are considering volume of distributional area. Volume of distribution area also we are taking consideration. Why? Because here we are administering our dosage form repeatedly. That means we can take 2 or 3 or 4 or n times either a day or for a week. So we are going to take repeated dosage for administration. For that reason, how much volume of distribution it will requires for particular area. So that's why you can replace this VD with the VD area. So then there is a coincidence with this one compartmental equations to the two compartmental systems. So only one thing you have to remember here. Generally, two compartmental open model drugs will have two types of hybrid constant. One is for alpha and one is for beta. Alpha is nothing but it will says you about the absorption rate, and in case of beta it is denoting you about the elimination. So for that reason, instead of taking beta here, we can take Ke. Ke is nothing but our elimination rate constant. So for rough approximations of the two compartmental parameters and plasma concentrations for IV injections, here they have written direct equations. Okay, you can learn these equations directly. So the drug which is following two compartmental open model, when we take such drug in the form of multiple dosing, in the form of repeated administration, through this IV injection or through the extravascular dosing, so how we can calculate the PK parameter? So here we can always consider the average plasma drug concentration. C stands for concentration of a drug in the plasma. So C average is nothing but initial amount, that is X naught. X naught is the initial amount of the drug divides with beta. Beta is nothing but Ke. Instead of beta you can write Ke also, elimination rate constant. That is also correct equation. And then VD area, you can write VD area. So like this you can write. Then tau. Here we are taking dosing intervals. Why? Because we are taking our dosage form in the form of repeated manner. So for that reason we will consider the dosing intervals. So you can find out the C concentration average with the help of initial amount of the drug and Ke and VD area and tau. So next one is loading dose. So how you can find out the beginning dose or initial higher dose of a drug? C average this is into VD area divides with e to the power of minus beta. You can write like this: C average into VD area divides with e to the power of minus beta t. Okay, instead of beta you can write minus Ke. So beta is always represents you elimination rate constant. This is time, not a time interval. This is time. Why? Here we can take only time. This is an initial dose, initial higher dose. So initially we don't have a time intervals. We have a particular time. We can take our dosage form. So for that reason you can take, instead of tau, only T, not a tau. Just remember the difference. Okay. So here we are calculating the equation for this loading dose. For that reason we can take small t, time, not a time interval. Okay. So then these two equations are for IV injections of a drug which is following two compartmental multiple dosing. Then you have extravascular dosing. Extravascular dosing, the C average, plasma drug concentration average is equals F of X naught. F is fraction of drug or fraction of amount of the drug can be available in the plasma. X naught is initial amount of the drug. Beta or Ke, VD area into tau. So the equation is same as that of IV injection. Only difference is here we have a capital F. Why? Because here we are taking our drug through oral route. So here there is a need to calculate our fraction of the drug availability, and then the loading dose can be calculated with the help of same equation as that of loading dose. Here this whole term can be divides with capital F. Here you just remember one thing, difference between IV injection and for extravascular dosing, we have only one parameter, that is capital F is there for this oral route of administration. So this is about IV injection and extravascular dosing. And then you have to calculate the accumulation ratio of the drug. R is ratio. R stands for ratio. AC is nothing but accumulation. So accumulated ratio of a drug is the ratio of loading and maintenance dose. Loading and maintenance dose. Here one thing you can remember, your loading dose is nothing but X star. You can write X star. Okay. X star. This is nothing but loading dose. And maintenance dose is X0. This is X0. So the accumulation ratio of drug, that is RAC, is the ratio of loading and the maintenance dose. So X star divides with X naught minus 1 divided by 1 minus e to the power of minus beta tau, not t, it's a tau. Okay, so X star is loading dose and X naught is maintenance dose. So you just assume your maintenance dose you will get at steady state level. So after reaching maintenance dose, the drug is going to be eliminated out, so that we can calculate minus beta tau. Simple thing. Okay, so this is what the accumulation ratio of the drug, nothing but RAC. So the rate at which the steady state is attained, it is depends almost entirely on beta. See, here after some time we may achieve some steady state. So this is totally dependent upon the drug elimination. Elimination hybrid is nothing but your beta. That's why the steady state which is attained, it will be totally depends almost entirely on beta, not on alpha. Alpha is nothing but our absorption hybrid. Okay, so the elimination process was happened due to of its beta, nothing but elimination rate constant. Then it will take approximately 5 half lives of the drug to reach the plateau level. Plateau level is nothing but your steady state level. Don't get confused. Plateau or steady state will be the synonyms. Okay, so it will take to achieve its steady state, approximately it can use 5 half lives of the drug. So using beta in the place of elimination rate constant in the equations, it can be developed for one compartment open model, allow us to calculate various pK parameters. So what is the use to replace your beta with Ke? So it is useful as to calculate various pK parameters of two compartment systems at the steady state level, at the plateau level. Okay, so this is what about the plateau level, loading dose and maintenance dose. And one more important thing, I collected some material from the net. So this is also very good. See, an initial or the first dose intended to be therapeutic is called as priming or loading dose. Is called as priming or loading dose. So you can calculate directly the loading dose with the help of CSS, steady state average plasma drug concentration into the volume of distribution divides with fraction of the drug availability. So you can directly calculate your loading dose from this equation also. If your drug will follows one compartmental open model, or else if your drug will follows two compartmental open model, you can calculate the loading dose for this one and two compartments separately by using this equation. Here you have VD, target. P is nothing but your peripheral compartment, target one compartment, divides with F fraction of drug availability. So here also you have volume of distribution, but here you have B. B is nothing but your central compartment, Instead of B, you can write C also. So volume of distribution of your drug at central compartment. So you can calculate directly the maintenance dose for first one compartmental model and for two compartmental model. And what is the objective of this loading dose? To achieve desired plasma concentration as quickly as possible. So here we are saying that this is the loading dose. So the beginning dose. So it is useful as to calculate the plasma drug concentration at desired. That means it is sufficient, it is enough. It is enough to produce its pharmacological action. Okay, not in the steady state. It is in the normal state only. After loading dose, when you give that maintenance dose, then it is at steady state. Your maintenance dose is at steady state, but your loading dose is useful to you for producing the desired plasma drug concentration. So these equations are not mandatory for you. And then what is the use of this maintenance dose? A maintenance dose is given to maintain and so that the therapeutic effect is also maintained. Okay, the ratio of loading and maintenance dose is called dose ratio. X0L divides with X. X0 is initial amount of the drug. L stands for loading dose and X0 stands for maintenance dose. So here X naught L is loading dose, X naught is maintenance dose. So the ratio between this loading dose and maintenance dose is called as dose ratio. So you just know the importance of loading dose and maintenance dose, why we are taking and what are the importance of this loading dose and maintenance dose. See here, when you take the plasma drug concentration on y-axis and the dosing interval on x-axis, see, we already know this MEC, minimum effective concentration, and MSC, maximum safe concentration. So our drug is going to be fluctuated between this MEC and MSC. In some cases, some drugs will fluctuate between the subtherapeutic level also. Subtherapeutic level. So the drug which is fluctuating between this MEC and MSC is called as therapeutic window. Right? So below this MEC level, we may call it as subtherapeutic level. See here, some pink lines, it is going to into this subtherapeutic level also. Here the dose ratio will be less than 2. This is a standard ratio. Here the dose ratio will be less than 2. Nothing but your tau dosing interval is more than that of T half. If your drug is having 5 hours of T half, you can take the interval as 6 hours. So it means the T half of the drug is more than that of your dosing interval. Okay, then in some drugs it will be fluctuated between this MEC and MSC. So the drugs which are fluctuating or which are showing its action between this MEC level and MSC level, those drugs are having dose ratio of 2. Dose ratio is nothing but loading dose divides with your maintenance dose. This is nothing but your dose ratio. Okay, so remember that dose ratio is nothing but loading dose divides with maintenance dose. Loading dose is nothing but X naught L divides with X naught. So here the dose ratio is 2 for the drugs which will exhibit this therapeutic window, and beyond the therapeutic window it will be greater than 2. That means the dosing interval is less than that of T half. Okay, for example, your drug is having same 5 hours of T half, your dosing interval is less. That means it will be decreasing. You can take 4 hours as an interval. So this is how the drugs will be fluctuated between these dose ratios and how the importance of this maintenance dose and this loading dose. See here, this arrow, this green color mark indicated you on this line. This why? Because this line will states you there is a initial higher dose response of your drug. Initial higher dose response of your drug. That is nothing but your loading dose. And here you have some peak, that is nothing but the maximum peak plasma concentration. So it is maintaining constantly, that is it is maintaining a steady state rate. You may call it as maintenance dose. See here, that's why this is called x naught, this is one other x naught, this is one more x naught, and this is one more x naught. So where the plateau, we will attain where the plateau, then we may call it as maintenance doses. This is what the relationship of loading dose and maintenance dose ratios. See here, up to this level we may call it as loading dose, and after this the response of a drug will sustaining, then we may call it as maintenance dose. See here, in case of conventional dose, this yellow color mark is prolonged release. This is one separate one separate modified drug release systems. See ma'am, you have conventional systems and novel systems, conventional dosage forms and novel dosage forms. Conventional dosage forms are also called as old type. We have tablets, capsules, normal suspensions, syrups. These all will comes under conventional dosage forms. In case of novel dosage forms, we have controlled drug delivery systems or prolonged drug delivery systems, or we have sustained drug delivery systems. All these will have one particular goal. What is that? It is having the capability to release your drug up to prolonged periods of time. So by the use of all these modified drug release systems, you can able to release your drug in the body up to over period of time. Then it will be avoiding your frequent administration of your particular dose. Okay, so in case of conventional dosage forms, you need to take one particular dose in 3 or 2 times a day. But in case of your novel modified release dosage forms, if you take one time also, the drug will be released up to prolonged periods of time in your body. So here we are avoiding frequent administration of your drug in case of novel, and here we need to take repeatedly, we need to take frequently your drug to produce its action. So in case of conventional dosage form, this blue color line is indicating you the conventional dosage form curve, and this yellow color is prolonged release. See here, up to this peak point, it is having this sustainability of the action, then it is beyond declining. Then in case of sustained release, the drug is having some peak up to its loading dose. At the your pharmacological action is going to be start. Here the loading dose can be applied. After that your maintenance dose will be produced at steady state. So here the drug action is sustaining. The drug action is sustaining up to prolonged periods of time. So that's why the name called sustained release. After attaining particular peak plasma concentration, which is enough to produce its pharmacological action, then it is sustaining its action. That means the drug is sustaining its action. So with this sustainability of its action will be achieved with the help of this maintenance dose at steady state level. And in case of prolonged release, we may not achieve proper sustainability in its action. So it is declining its drug concentration. Okay, after certain time period, it is declining its action. And in case of conventional dose, directly getting peak, then it is directly going down. There is no sustainability and there is no drug release up to over period of time. It is just after taking your drug, then it is elucidating its pharmacological action, then it is going to eliminate it out. There is no need to resides in our body for over period of time. Okay, plot showing the effect of loading dose and maintenance dose for particular modified release dosage forms. So you have this much importance by using this loading dose and maintenance dose. So you have to write this loading dose, maintenance dose importance also while writing your two compartmental open model through multiple dosage regimen. So next part is, this is also for IV injections. Okay, so one thing you can remember, every time you have to take the average concentration or else the average amount of the drug. This is concentration, this is amount of the drug. So till now, we learned about maintenance dose, loading dose, that is for extravascular, that is for IV injections. So this is also same thing, the IV injections, but this is in terms of amounts. We have learned in terms of concentration, but this is in terms of amount of the drug. X average is equals X naught divides with KE tau, okay, and then X average is equals C average into VD. This is nothing but X naught into K tau. Wherever your K is there, you can remember that, that will be KE, elimination rate constant. See, this is X average and this is also X average. And finally your X average, that means the amount of the drug which is available in the plasma, average amount of the drug which is available in the plasma is nothing but your loading dose, is nothing but your loading dose, and then which is administered before your maintenance dose. X naught is nothing but your maintenance dose, right? So X star is nothing but loading dose which is just before to administer your maintenance dose. So first you need to administer loading dose, then you can take maintenance dose. So your X star is nothing but the loading dose and X naught is nothing but the maintenance dose. The amount of the drug eliminated from a loading dose, the amount of the drug eliminated from a loading dose. So loading dose is nothing but our initial dose, right? So here you can take some time intervals, 1, 2, 3. So these are called intervals, no? That's why we are representing with tau. So the amount of drug eliminated from your loading dose, the amount of the drug is getting eliminated at the time interval tau, which is equal to the difference between the loading dose and the amount remained in the body after tau. So this difference of this dosing interval will denoting u, or which will be equal to the difference between the loading dose and the amount remained in the body after taking tau. So here we are taking 2 to 3 doses, right? This is first dose and this is second dose and this is third dose. With respect to the particular dosing intervals, we are taking our different dose levels at different time intervals, right? So here after removing this, we are taking this. After removing the second dose, we are taking third dose. So that's why if you want to get how much amount of the drug will get eliminated out from the loading dose at the time interval tau, that is nothing but first time interval tau, which is equal to that, the difference between the loading dose x star which is nothing but the loading dose, and the amount remaining in the body is nothing but after taking your second dose, some amount of the first dose of your drug is remained in your body. So that will be gets equal. The remaining amount of the body after particular time interval is nothing but your X average, amount of the drug, average amount of the drug. So then amount of the drug is eliminating out at loading dose. Here we are talking in the sense of loading dose. That is nothing but X star minus X average. So X average means what? The amount of the drug remained in the body after particular dosing interval. So how much amount of the drug is remaining and how much amount of the drug we are taking. Then you may have X star minus X star into e to the power of minus k tau. X average is nothing but X star into e to the power of minus k tau. Why? Here we are taking the difference between the loading dose and the amount remaining in the body after particular time interval. So that's why this loading dose is multiplied with how much amount of the drug remaining in the body. Remaining amount will denoting you in the sense of elimination rate constant and in the sense of time intervals. Okay. So then your loading dose is multiplied is you have to, this X star is the similar one, same thing. So you have to comma this X star, then 1 minus e to the power of minus k tau. So this is the final equation for amount of drug will gets eliminated. So here X star will same. So we are taking out this X star, then we can write 1 minus e to the power of minus k tau. That is nothing but amount of the drug eliminated out. The amount of the drug eliminated should be to the maintenance dose X naught to maintain a steady state level. If the drug is eliminating out, what does it mean? It is having the capability to maintain the dose of X naught. Therefore, maintenance dose X naught is equals X star into 1 minus e to the power of minus kt. So here X naught is nothing but maintenance dose. See ma'am, our drug is eliminating out. So here our drug is eliminating out means which parameter is involving here? Our maintenance dose is involving. Our maintenance dose is nothing but our X naught at the steady state level. This is common. So therefore your maintenance dose, if you want to get your maintenance dose, first you have a loading dose, that is nothing but your X naught, then which is multiplied with 1 minus e to the power of minus k tau. From where we will get this equation? From this equation. Amount of the drug is eliminated is nothing but X star 1 minus e to the power of minus kt. Okay, that amount of the drug is eliminating out because of the maintenance dose. So that amount of the drug eliminated is nothing but your maintenance dose. That's why therefore X naught is equals same equation as above. Then from this you can calculate the loading dose, that is X star. X star is equals initial dose which is divides with 1 minus e to the power of minus k tau. The elimination rate constant Ke, volume of distribution Vd, dosing interval tau are used to calculate the loading dose also. We have two equations here. This is maintenance dose and this is for loading dose. But Vd and tau and Ke is also useful to calculate as loading dose and maintenance dose. For that they have written two more equations. See here, loading dose with the respectiveness of this Ke, Vd, tau. X naught is equals to X average divides with e to the power of minus k tau. X average is nothing but C average into Vd. Why? Because we have an equation X is equals to Vd into C. So instead of writing XAV here, we have written CAV into Vd because we have equation like X is equals to Vd into C. This is the apparent volume of distribution equation. We have a relationship with plasma drug concentration and the amount of the drug available in the plasma. So that's why we have written instead of XAV, CAV. Vd. So this e to the power of minus k tau is same. This is what? The loading dose. And the maintenance dose, that is nothing but X naught is equals maintenance dose into 1 minus e to the power of minus k tau. Okay, these two equations are written with respect to the Vd, tau and Ke. The ratio of loading to the maintenance dose, which is depends on the dosing interval and the half-life of the drug and is equal to the accumulation index. RAC is nothing but ratio of accumulation index. R stands for ratio, AC is accumulation index. X star is nothing but loading dose. X naught is nothing but your maintenance dose. That is 1 by 1 minus e to the power of minus k tau. If you did not remember this equation, at least you can write RAC is equals to loading dose by maintenance dose or X star by X naught. Okay. So this is what your loading dose, maintenance dose, and equations for extravascular administration and for IV injections for the drug which is following your two compartmental open model for this multiple dosage regimen. Okay. So this is what your fifth unit. With this topic, I completed total fifth unit. Only one thing, important thing you have to remember, based on the biological half-life of the drug, we can take the dosage form repeatedly. After removal of first dose, we can take the second dose. But each and every time, we have to maintain the same dose level. Suppose we will take 100 mg for the first dose. Okay. So only 90 mg is absorbing and 10 mg is leaving. That means 10 mg will be remaining in the first dose. And the second dose, again you have to take 100 mg. Why? Because doctor prescribed you every time you have to take 100 mg. But the therapeutic activity of your drug may attain at 1 gram. That is nothing but at 1000 mg you may get some therapeutic effect. So here we have remained amount 10 mg, and next time again we have to take 100 mg. Then here 10 mg of first dose, which amount will be remained? Then here 100 mg. From this 100 again 90 mg only absorbed. Then again you have 100 mg. So with that you can take n number of doses up to at what amount, at what timing interval you may achieve your 1 gram. Then it is useful to produce a therapeutic effect. Only one thing here, we are taking the drug in a repetitive manner. After eliminating our first dose, we are taking our second dose. Unless we will achieve proper therapeutic effect, we can take our dose in a repeated manner. This